Okay, good morning. This is the 8th class time, and this is the last. Well, thank you very much for, ちょっと待って、なんか自分の名前書いてる。for attending, and ちょっと待ってな。早速。I'm now sharing the screen. OK。こうして、PowerPoint。こんな風にして、さらにして、ちょっと待ってね、スライドショー。Okay. Okay. Not yet. Wait a moment. Okay, this is the number 8. And today's topic is about the focusing on the countermeasures, how to prevent the natural disasters. But I think that we are focusing on some kind of the natural disasters, mainly induced by water or heavy rainfall. So yes, today's last slide I prepared last to do it. Okay. Yeah, so countermeasures for the natural disasters, but especially for some sediment disasters, that means some flood or heavy rainfall and the slope failure. Such kind of the countermeasures, how to prevent the disasters. So we have some works, method to prevent them. And yes, we would like to think of some laws for natural disasters, especially for the Japanese laws for natural disasters. So, okay, so today's topics are about, countermeasures, laws, and we would like to learn about some evacuation. So that means alert system. And first of all, we will learn factor of safety for slope. So last class, we have learned about some very basic soil mechanics and some how to estimate the soil strength by C and phi with some parameters of the soil. But it is very basic one, and it's not it's okay. But today, together with the slope failure or soil strength, soil mechanics, we'd like to learn about the factor of safety, some concept of the factor of safety. Yes. So today's topics is like this. And the sediment disasters, as for the sediment disasters, we can classify some categories. So, such as landslide. Yes, landslide is kind of the very basic terms, because you can see that the land, yes, it's a soil of earth, will be sliding. So this is very typical word, landslide. But as for in terms of the natural disasters, we use these words. Such kind of the landslide is meaning of some mass, very large area will be sliding slowly. It's the landslide, or we are using the words such as landslide area or something. So this is some bigger slope moving with, especially for slow speed. But sometimes we use some other words that the rapid landslide. So that means the speed of the landslide movement is higher. But yes, Landslide is a kind of a very slow movement and wider area. And the debris flow, the middle is the debris flow. Debris flow is a kind of some small collapse of the slope, and it will be discharged to the downstream with some kind of the mixture of the water and the soil. So it's a very dangerous because water meaning very flowing rapidly and speedy, and the soil means the density is very high. So therefore mixing with the soil and water is a very that has much energy and flowing down, and sometimes it make very big disasters. And it is some kind of the detaching of the rocks. So cliff collapse is a kind of some detach of the mass or soil. So we can classify these three patterns about for the sediment discharge or sediment disasters. And now we would like to focus on to the safety factor of safety here, and about for the landslide area. Landslide area has a very large area and moving slowly with water. So you can see this is the groundwater table, and when the groundwater table is rising, then the slope will be moving. Stableness, it becomes unstable because of the rising of the water. So this is some kind of the review of the previous last classes, why the land will be weak and it become unstable with the groundwater table rising. It's this, and this shows some graph of the strength of the soil, and the strength of the soil is at the same time it's the meaning of the stability, slope stability, or slope strength itself. So this is some graph, right? And we have the two parameters, C adhesive force and phi the internal friction angle. And this vertical value is calculated like this. This is, we can read this tau equals C plus sigma tangent phi. So, and the sigma is the x-axis, it's the normal stress, some force to the perpendicular to the slope. So this is the graph. So it is very basic of the soil mechanics that is very important. So let's review this. And as for the adhesive force, this is some Kaonyao power. Kaonyao is okay. Yes, sticky rice is sticky power, and the Kaonyao, yes. Adhesive force and soil and water. Water. Okay. Okay, so soil and water and sticky rice, Kaonyao or some adhesive means the water is just water like the very narrow space, and it has some surface tension that the water surface has some power to shrink itself, its surface. So this shrinking power becomes the binding power to each other, or you can you can understand that in summer, when we have the perspiration sweat, then the t-shirt will be touched with our body. So that is because of the sweat, because of the water between the t-shirt and the skin. Then the t-shirt will touch some adhesive force. So water has some glue power to bind itself by the existence of the narrow space between each particle. So yes, previous slides. Last time I showed some picture of the sand ball, and the sand ball, we can make sand ball with good water content, not too dry, not too wet. Too wet, we cannot make the sand ball, but some sand with some water, it's okay. That is this condition. So too dry means the water is vanishing. So nothing have some adhesive force, glue-like power. And too wet means the completely wet, that is called saturated. So saturated means the filled with the water. The space is filled with water. So no water surface. So no water surface tension. So soil is again detaching, going apart and apart. So this is adhesive force has one end. And the next one is the internal friction or that is a kind of the phenomenon of the friction. So it's a very simple. So I will I will delete some precise example explanation, but the friction has some resistance between some material and material, and the friction, yes, there is the friction, and much friction has generated by much power. Yes, this is high friction resistance, and the low power has low friction. And yes, we can see the figure again. Figure again, this graph again. Then we can say that if the pushing power is higher, then the friction power is high. Friction power is here. Sigma is the normal stress. Normal stress is the power pushing to the perpendicular to some plates. So if the power is higher, then the friction resistance is higher. And as for the normal, at the actual situation, yes, surely we have some slip surface. It will be slipped something potential line. It will be slipped here. And yes, we have the soil, and for be easy understanding, we can think of the soil material here, soil layer here, and this has the mass, and the gravity energy make mass of the M and Z. Then it will be this particle want to slide this direction, and again at the same time this material is pushing the slope to this value. So mz will be if this is the vertical one, and this is separated with the parallel to the slope and perpendicular to the slope. And this is the slip power that this soil want to slip here. And this material is pushing itself to the soil as this power force. And yes, slope is, of course, it pushing up this material, and the friction power is the same if this is not sliding. So in this graph, we can say that now we have some soil material mass, weight, and that is some kind of the sigma. ちょっとこれやっぱ書こうか。ちょっと wait a moment. Again. What happens when the wet, when saturated or groundwater table is rising? Again, this is just kind of a review. Which is phi is this angle, and tangent phi, yes, we can generate this relationship with this graph, but I delete this explanation. That the tangent phi means the mu of the friction coefficient. So now the soil mass is some kind of the mass weight. Then it has the weight. So this weight is, for example, this point. And yes, we have actually coefficient force. So now the soil or slope is resistance force to be sliding at this value. But when it is wet, first the coefficient power, adhesive power will be there because the sandball will be attached or broken with the saturated situation. So it will be, the relationship is changing like this. And not here, but the when the wet groundwater is rising, then the groundwater level here, then there is some floating power, floating force, buoyant force. So it will be that weight is, yes, actually the weight does not decrease, but the with the buoyant floating force, the normal state will be lower. So weight will become here. It's a normal situation, and that the groundwater level is higher. Then the strength of the soil or strength of the slope will decrease. So that is the mechanism of the slope failure happens. All right. So this is the graph, and back to the this situation is kind of some landslide area. So this is sliding with some shape of the arc. This dotted line is the slip surface. Yes, landslide area is continuously moving a little, moving. So some slip surface is concreted. This is some, yes, actually this is the line or phase for slipping. And then sometimes the groundwater level is rising. This is the mark of the surface of the groundwater table. And the groundwater level will be higher. And then floating power and the adhesive force will decreasing. So this mass, soil mass will be moving. And yes, now we would like to omit the detail, but we can consider of these force balance by cutting like these square, many square. You can see the some. This is triangle, but the square. Yes, cutting vertically. Then we can calculate the balance of the power, moving power, and the resistance power. Then we can estimate the total balance of the power. So yes, so the formula is a little bit complicated, but it's very basic. And small L means some line legs, line here, but you can see that the C and Y are tangent Y, and this is a kind of some floating power or something. So anyway, we use sometimes Fs, that means factor of safety as resistance force at the upper side, and the lower part is a sliding force. So if okay, so Fs equal 1, it is some very critical, very some kind of unstable, but it's about to sliding, but it's not move. So that is the resistance force and sliding force is equal. And if the Fs is over 1, that means resistance is larger than the sliding force, then we can say that is safe. And this value Fs is below 1, that means the sliding force is much higher than resistance force. So we can define the factor of safety like this. And this would be calculated with the sliding force. Sliding force is a kind of the mass volume, but mass weight sliding. And resistance force is a kind of the adhesive force adding the friction force. So that is this part. So we can say like this, and we call this is factor of safety. So yes, but 一回りしただけだな。sometimes it is easy or sometimes it is difficult because if we know well about the slip surface, where slip surface is, if we can estimate where the slip surface is, then it is a little bit easy to think of this formula because we can divide it like this. But for example, yes, landslide area has some continuous moving, so we can estimate the boundary of the sliding area, and we can estimate some gaps of the sliding area, or sometimes we use some boring test. Boring test means we dig a hole with a heavy machine and digging some and collecting the soil sample, and we search where is the slip surface with the boring core. あ、ちょっと待って、ボーリングコアちょっとあったの。ボーリングコア。待ってね。出てこない。あ、これ。あ、yes, you can see this with the turning to the top of the left is the top. And the boring core is like this boring core sample. And then it is a kind of fragile, but the expert can detect where the sliding surface is, because there is some clay-like point when the sliding is happening, because sliding means some, yes, the soil and the soil will be slided, shared, and it becomes some mark to sliding. For example, it will be not the rock itself, but it will be become clay soil because of the shared with each other. And sometimes we can see some mirror-like plates inside the boring core. So so this is a core sample, and we took some core sample, part of the core sample, and when the slide surface is there, then we can see some mirror-like mark with line, because sliding direction is here. So this is the sharing. Then the surface of the soil is polished and become clear and mirror-like shape. So we can find where is the slip surface with this boring sample. Or we can use this formula. For example, yes, we can start with Fs value. For example, we detect this area is moving. Yes, actually there is some mark, fingerprint of the moving the landslide. The slope is moving. Then the factor of safety would be 1 or 0.95, because it is sometimes move and sometimes stop. So very severe situation that must be Fs value must be 1.0 or 0.59. Then we can do some back analysis of this figure formula. So we will estimate the phi and c with some kind of the soil test and c and phi, and then we estimate the slip surface depth, shape, and depth. Then we can calculate the detail of the soil situation, for example, C and Y at the slip surface at this area. So we can use this formula as the back analysis to understand what happened at the landslide area. So it is very difficult to calculate this factor of safety if the slope is stable. Then we can estimate or check some soil tests and detect check for laboratory experiment. For example, C and phi would be checked with the laboratory test by taking the soil sample and estimating the slip surface at the stable area. Then we can calculate this factor of safety. But this is usually used for some unstable area. And if the unstable means the Fs is 1.0 or 0.95, then we can use this formula and do back analysis to check the accurate slip surface and some estimated phi and c. And we also use this formula by the countermeasure. So we would use some value of target factor of safety, target value of the FS. So we now I am introducing you some countermeasure works, and we have some target value of the FS, and for example, we would like to do the FS value as 1.25 or 1.5. 1.5 is a little bit much value, so target value FS is 1.2. So we have to do this amount of countermeasure work or something. So this is something indicator for doing the countermeasure. Or if this area is moving, then we can assume that the FS is 1.0 or 0.95. So we use this value like this. All right. And this is some kind of the review of the last class, that the groundwater rise. Then we have the buoyant force, it's floating force, upward pull, and that adhesive force is reduced. Then so groundwater rise. Then the final station has not been written that yes, groundwater rise. Then soil slope will be collapsed. Yes, like this. Okay. This is some cartoon explaining the countermeasures. So very famous and important countermeasure for protecting the landslide is drainage work. Drainage work. Yes. Drainage work, and yes, drainage work with drainage pipe and boring. Yes. Countermeasure. Yes, countermeasure for landslide. So yes. Again, here that the main cause that landslide happen is the groundwater, especially for the landslide area. Landslide area is wide and continuously moving slowly and slowly. And so, you know that this kind of the disaster is a very slow disaster, slow speed. So we have, for example, village, road, or some facilities at the landslide area. So we need to stop the moving of the land. So, and the cause of the slide is groundwater, especially. So we can remove the water. So it becomes stable. So it's called drainage work. And very simple that we can stick the pipe. Pipe has the many hole to the edge of the or middle of the pipe with a pipe with a hole that we can exclude, remove the groundwater. So it is okay to make stable. So this is very simple and drainage work. And sometimes we use some connection of the drainage pipe. For example, this is this is showing some cylinder-like pipe, but this is vertical pipe, and this is a little bit bigger. And stick the pipe horizontally like this, and stick, this is a drainage to the surface, and or some very simply the horizontal pipe, and this is called horizontal boring, and remove the water. こっちが先がいいかな。ちょっと待ってね。And I said that we made some vertical pipe, cylinder-like, And this is a picture of that one, typical one. And can you estimate the length? But yes, surely this is big pipe, vertical pipe. And yes, we have a lid because it's danger if we do not have the lid. Some child will be entering, naughty boy will come, so we need a lid. And but this is some vertical hole, and maybe 4 meter, diameter 4 meter, radius 2 meters. So, surely 4 meter, because we need to dig some horizontal boring inside the hole. So we need the size to install the machine to dig the hole inside in the hole. So this is a little bit larger one. And this is some experimental board that and it's showing that vertical hole and the horizontal pipe and connecting like this. They are together connecting. So this is vertical, very, very bigger picture. I showed the picture that bigger one, and this is connected horizontally each other, and then it will be exploded to the surface. This is pipe work, drainage work. And this is also pile work, and anchor work is here. And the red line is estimated slip surface. Yes. Here in Japanese, that it's explained that it is about 50-meter depth. This length is 50-meter estimated. Backward. And this is some document that I have. I went some meeting conference. Maybe this is me. I'm not sure, but some person is me. But this is some meeting for checking the landslide area. And at that time, this is some program that this is the lid of the vertical hole, and here this vertical bar, it's a little bit bending. So yes, we installed this drainage hole, but yes, this is the landslide area, so some power will be some power make the change of the shape of this vertical hole. So it's a little bit dangerous situation. So this is some kind of the topics of this conference. Yoko boarding. Yes, this is a picture of the vertical one, and the inside, very bottom of this hole, we dig some horizontal pipe. And at some very bigger landslide area, we sometimes use the tunnel. Tunnel beneath the landslide area. So this is a very deeper area. So the board is showing that drainage pipe network and the surface surface. This is the surface, and make the very big hole and the horizontal pipe and the drainage work. This is some kind of the drainage work, and the tunnel is here. 難しいな。It's very difficult to draw, and from the bottom they stick the pipe and collecting water. So this is a kind of a tunnel work, tunnel to drawing, collecting water by penetrating pipe. Yes. So you can see that this pipe. Can you see this pipe? It's a kind of some sticking to the landslide material, soil layers, and collecting the water with this tunnel, a very long tunnel. Sorry, I forgot where this is, but it is some area we use tunnel to collect water. So collecting water is very important countermeasures. And other countermeasures here. So yes, surely you can see these facility, these work at some road constructing. So sometimes road cut the mountain, and we make stable the slope with this lattice-like frame, and this is anchor work. So now this machine, this is also just the opposite direction. Yes, digging some hole like perpendicular to this slope, and this is the cartoon of this anchor work. This is the framework, and it makes stable the surface of the slope with this lattice-like frame, and the center of the frame has the anchor, and now drilling and digging some hole like this, and this is the anchor top. So you can see at some highway or some road, you can see the top of the anchor. This is is top here, head of the top. This is called cap of the anchor, and this is drilling the hole, and here we put cement like glue. So this is stable point with some strong cement, and this is connected to the bedrock. And this cap is some screwed. We can screw this cap, and then it is screwed and fixed with the anchor. So anchor means need some cement, concrete to fix here, and screwed at the top. So this frame is concretely fixed with this frame and anchor. So we can see the anchor top like this, anchor cap. Yes. And another one is this is the pile work. Pile is some bar. Bar is sticking into the mountain. Yes, we have the picture of the pile work like this. So pile is, yes, you can see the pile top here, and now drawing this pipe to the vertically with this machine. So it's simple. It's like a pin fixing something on the wall. It's just the same meaning that the pile is sticking, and this is a slip surface and moving material, and beneath of the slip surface is some concreted stable point, so we can stick some needle, but it's actually large, but this is the pile work. Pile is sticked. And sometimes we make some deformation, changing the slope shape, and for example, cutting for the material for moving, or some putting the soil at the bottom of the slope. Then this becomes a weight to the slope, and removing this means that the material, slope material will be reduced. But this is a little bit difficult work to cut the soil. So, for example, it's often happen in Japan that for example, cutting work. Yes, we find somewhere landslide area. We found some slope landslide areas here. We found this, and this is inside soil, but we can see the boundary at the surface. So surface, we can find the mark of the grading. So we can estimate the landslide area. So it's so dangerous. So let's cut and reduce the volume of the landslide. This may be stable. So removing is better measures, and this is easy to do to remove the soil. So yes, this is some good countermeasures. But when it cut the slope material here, then new slide has happened. So this material is surely now it's the top of the landslide, but it may be the bottom of the potential landslide and the weight of for this slide. So sometimes another slide will happen with the cutting the soil. So this works is very easy. Cutting and putting is very easy. This cut is put here, so easy, but it also dangerous works because we need to survey, we need detailed survey for the surrounding of the situation. So cutting is one work, but a little bit difficult work. Surely the technique is also needed, but yes, we need to survey precisely. This is a picture of the pile work. Yes, like pile work. Yes, you can see the human man here. So pile, yes, like pin. I said this is like pin to the wall, but actually this is a big pile, big cylinder. Can you see like this? This is some kind of the sample document that I have some meeting for the checking of the landslide area. And this is the document at that meeting. So, but here we can check the landslide block like this and make some digging many holes around here. Then we checking this line, this line, this line, this line. So like this. Yes, this is just the document sample. And you can see some shape here. This is a area of the vertical, horizontal pipe work. And center is we have some very big hole. And to the upstream, we stick the pipe, and this is the pipe area, pipe sticking area. And we drained, collect water and reduce the groundwater level. So there are many pipe work here, drainage work. Yes, this is the boring sample, for example. So this is the picture of the some landslide area. Sorry, this is Japanese. Yuzurihara landslide area. Yuzurihara is a southern part of the Tochigi, no, Gunma. It's a very boundary of the Saitama prefecture and the Tochigi, Gunma. Shimokubo Dam is this is my picture that I'm standing on the Shimokubo water dam here, and we look the downstream, and this is the landslide area. And can you see that here is the Yuzurihara, and you know that yes, this is not a steep slope, but the rather gentle slope, but this is landslide area. And you can see some line here. This is some boundary of the top of the landslide, and the sliding top head is here, and sliding to the downstream to the river. And this is the village. So yes, landslide is a little bit yes, it's a very important point, because I said that landslide will happen with the groundwater level, groundwater rising. So that means, yes, groundwater rising. So that means there is water. So it is very good to live if the land is not sliding. So yes, sometimes landslide happening. So landslide means it's sliding. So, and we have the what this is the much of the water. So it is a very flat area. So landslide area is very easy to live in, because we can get the water, and it is comparatively the slope is gentle. So yeah, village. Yes, we have village at the landslide area, because it is very easy to live. Except the landsliding. The landslide sometimes happens, and normally it stops. So normally it is safe. So landslide area, it's easy to cultivate something, rice or something. So you know that the Canada. Sorry, I didn't know the English, but the paddy field with the terrace paddy field. In Niigata Prefecture in Japan, we have many rice field, and we have also the terrace rice field, and somewhere of the terrace rice field is the landslide area, because it has much water. They gather water, then plenty of the water, and the slope is rather gentle. And if it will be moving and changing, but the farmer will change the shape, and then some terrace paddy field at the slope will be generated at the, especially in Japan, Niigata Prefecture, we can see some terrace paddy field at the landslide area. So yes, so landslide area has the much water, and we have to reduce the groundwater level, but it is simultaneously, it's very easy to live in. Yes, so you can see the village at the Yuzurihara here. So a little bit slope is gentle, but you can see some houses here. Houses here. Yeah. Flat area here. This is the top of the landslide fault, and this is sliding area. And yes, you can see that this is very gentle slope, but this is gradually moving. So you can see some crack at the wall. This is usually have a direct deformation. The basement is cracked, so it's gradually moving. And this is just actual picture of the horizontal drainage pipe and sticking this bar and exclude the water. But you can see that the water remained here and no water. Yeah, but we can see the moss, so it's wet. Yes, surely this mark means some water is collecting. So yes, we cannot see that it is good pipe or not good pipe, but we cannot estimate where is the water certainly. So some pipe has much water collecting, but some is drying. Yes, but this is horizontal pipe work. And you may be seeing sometimes like this, right? This measurement, counter measurement, you can see the wire and the inside the wire, wire box, yes, wired box, and inside the wire box, we set the stones here. So in Japanese, we call this jakago. Ja means a snake. Jakago, kago means the box. So snake-like box. This is some snake-like. Or we call this 布団かご。布団英語で布団いや、布団。sleeping bag っていうのかな。sleeping bag or ジャカゴ。布団かご、ジャカゴ。In Japanese, that means some snake-like box and 布団 like sleeping bag-like box. Yes. In English, it is called gabion. ここに書いてあった。スネークバスケットケージ in Japanese. Yes. This is this point is the very bottom of the landslide area, and we use this wall-like countermeasure rock, and this is used because the slope is continuously moving. So it is originally straight, put to the straight, but this area is moving a little bit. So it pushed this box, gabion. So it's a little bit changing. And if we make some concreted wall, then concrete will be broken because the land is moving. So concrete wall is not good for using the moving area. So this is moving, but the gabion is changing the form, but the weight is still here. So concreted wall would be not useful when it is broken, has some gap, then it doesn't work. But this gabion can work even if the land is moved, gabion shape is moving. And it can be said that if you can see this gabion wall countermeasure, then this area will be dangerous. Now it may be moving. So that is some mark that it may be moving. So then we use this Jakago gabion work here. So gabion work is and we also use this inside the riverbed and to to make stable the riverbed or something, but they are used because it is not stable place, and it may be okay if the gabion is a little bit moving. So this is just the deformation of the gabion. Originally, this is straight. Okay. So now we would like to check the countermeasure for the debris flow. And debris flow is a kind of some very dangerous movement of the mixturing of the water and soil, and the speed is very high. So we need much countermeasure work like this. And erosion control dam is a little bit important one, but not only one single facility is not good because the debris flow has much energy and much amount. So single facility is not work, but some multiple facilities needed. Erosion control dam, yes. Yes, so yes, surely right. And this is some cartoon of the erosion control dam that yes, it stop and stop the debris flow, and simultaneously it is functions as stopping erosion, because we call this check dam or erosion control dam. If we do not have this check dam, then riverbed will be eroded, and again eroded. Then some new collapse failure will be happen. But when it can stop and stock the material soil, then no more erosion will be happened. So that is a very important point that you know that once it will be filled with the soil and material, but it is not the end of the function of the erosion control dam, but it is still working for preventing erosion, riverbed erosion. So this is very important. Yes, erosion control dam. And yes, we need the multiple facilities needed, and some erosion control dam has the open type and closed type. And because it is very difficult point that surely we need to stop the debris flow to reduce the dangerousness at the downstream. But at the same time, we need to bring stone or sand material to the downstream, because it is the natural situation that the soil and the rock will be moving from the upper part to the lower part. So if we stop every stone, the rocks, then the river downstream will be no stone and no sand, and it was so not good situation for the seashore, or at the seaside. We do not have the sea coast, because sea coast needs the sand from the river. So sea coast will be thin if we stop the stone completely. So we need to move down the stone and sand, and we have to reduce the energy of the debris flow. So last time I need to show this, and this is some movie to run the function of this erosion control dam. This is a good simulation model. Left one is the erosion control dam. The right one has the erosion control dam, and it's stop some debris. And the soils are going down safely to the downstream. And so you can see the multiple erosion control dam, and it reduces the energy of the debris flow because, for example, this is some simulation in mind that if you have the ball and the rolling to down, then it has the gravity force, then the speed is accelerating and more. But if we have some erosion control dam, and the erosion control dam can stock the material, then yes, this is the upstream and downstream, but you know that the ball will be reduce the energy because there is some flat place with the erosion control dam. So this is some important erosion function of the erosion control dam, that this erosion control dam reduce the energy of the debris flow. Without this, the ball will be accelerated and the speed will be higher and higher. But with erosion control dam and the soil is stocked, sediment is stocked, but it can reduce the energy of the debris flow. So some people think that when the erosion control dam has filled with the some sediment, then this function is finished, but not finished, but continuously this erosion control dam has some function. First that the erosion debris flow energy will be reduced, and they stop the potential erosion. Without the erosion control dam, they may be progress some erosion and become deeper and deeper, and the new collapse will happen. But this multiple erosion control dam make stop the riverbed erosion. So this is very important function for the erosion control dam. Next is the evacuation and the alert system. Evacuation and alert system in Japan, yes. This is an example sheet at Fuchu City and the hazard map for the flood. And you can see that this is the Tamagawa River. And you got T80 here. Yes, T80 here. So surely along the Tama River is very dangerous for the flood. And but we can estimate what happened at the flood. Some levee break. When the Tama levee break, this would be the dangerous area. So we can estimate that this flood hazard. So as for the flood hazard, T8 is okay for the flood hazard because this is a little bit elevation is higher to the Tama River. But we can some government distributed this hazard map. For example, this is the flat hazard map for Fuchu. Okay, yeah, this is some of the alerts. Yes, it's a kind of the alert system. Yes, hazard map. For example, flat. And here in Japan, we have some Amedas monitoring system that is the weather monitoring system. This is a meteorological Japan Meteorological Agency can check the rainfall or temperature or something. Mainly rainfall. So this is the in Japan, this is started from 1974, and we can get the data from 1980s. Yes. So this is the point of the Amedas situation. So in Japan, we have this point, 1,300 points, about 1,300 in Japan, and these are points like this. And Fuchu is here. So Fuchu here. This is the Fuchu Amedas. Jun-san did see yesterday. Do you remember? Did you remember? Yes. Okay. And there is the こっちだね. Yes. Amedas Fuchu, you can see easily at the nursery and in this campus. There is a Fuchu Amedas point. And this point has the rainfall meter, temperature meter, and wind meter, wind direction meter, and the sunshine meter that how many hours sunshine. So that's the data, and this is a little bit bigger Amedas point, and some Amedas point has only rainfall meter, rainfall only, but the Fuchu has the temperature and wind speed or something here. Next is the Zoom version. Rainfall meter, temperature meter here, and the wind speed and direction, and this is some meter to check the sunlight or cloudy or fine day. This can check the sunlight. This is Amedas point, 1,300 point inside Japan, all around Japan. And another one is for rainfall, is a radar rainfall meter. So we have 26, sorry, I'm not sure that the radar rainfall meter that this can emit some wave, and they can detect how many emitted wave will be go back. Then it can estimate the area distribution of the rainfall, and this circle that one radar rainfall meter is covering, and 40 years ago, 40 years ago, we have only one radar on the top of the summit of the Mount Fuji. So because you know that the Earth is a sphere, so and the Fuji sides are like the center of the Japan, and surely radar would like to check the typhoon path. So this is for the Pacific Ocean situation. So only one radar rainfall at the Fujisan, top of the Fujisan. But now we have 26 distributed radar rainfall, and the Fujisan radar is now removed, and we can check the distribution of the rainfall. And at the Amedas point, this is a very basic and very precise data will be acquired for the rainfall because it has the rain gauge meter. And the Amedas, radar Amedas is just the kind of the signal of the wave. So we can calculate the radar, comparing the radar value and the Amedas rain gauge meter, rain gauge at the surface, and we can recalculate the precise rainfall distribution. So this 26, 26 ここに書いてあったの。Yeah, 26 radar rain gauge can detect some distribution of the rainfall like this. And nowadays, we can get the rainfall data through smartphone, and it using this radar rain gauge and more precise radar rain gauge meter is now installed, preparing, and that is called X-band multi-parameter reader, and this can more precise and the resolution is very good. So nowadays we also using this new type of the rain gauge radar rain meter in Japan, and this is a kind of the estimation of the disasters, sediment disasters, slope failure or something. So yes, surely, roughly I will explain this, that the vertical value is some rainfall index, horizontal one. Vertical is also rainfall, but the horizontal is some rainfall index, so for long time, and the vertical one is also rainfall index, but it's a short time, for example, 1 hour rainfall, or for example, 24 rainfall or something. So then we can summarize the historical data. This situation, no failure has happened, and this situation, failure has happened. So we can get line, this some critical line, no failure happen and some failure happening with the rainfall index. And we often use the horizontal one. It's some shorter time index, and the vertical one is a longer time rainfall index. And those two are also the rainfall index, but the short time index and long time index, then we can usually get line like this. This is some critical line method by rainfall. Okay, we deleted this, omitted this. And nowadays we will use the short time rainfall index and long time, a little bit long time index is a little bit changing, but yes, let's omit this, skip this. And like that, we can get the rainfall data through the Amedas rain gauge and the radar rainfall meter. Then we can take the short-term rainfall index and the long-term rainfall index. Then in Japan now we are doing some level information, and this is a safe. Sorry, this is Japanese, but level 1 is a very safe, and level 5 is a very dangerous level. So we will use this alert system by the Japan Meteorological Agency. For example, nowadays we are use the level 4 and 5 is a very dangerous level degree, but the 5 will be the some level that some failure or some flood will be happening now. So estimated the disaster will be happening already here. So, so weather agency, meteorological agency appeal, make some level is presented, but we need to evacuate it when the level is 4, and 5 is a very dangerous situation. Now this system is used in Japan, and we can get this information from the web, internet. So, this is a very important information for you that if you are living in Japan, that JMA is the Japan Meteorological Agency, and the risk degree will be, you can check the degree of risk through the website. So you can get this information through smartphone. Kikikuru is the Japanese name of this. And this is some screenshot of the PC, and maybe this is smartphone. So Kikikuru is for this HRL. You can check the map that, for example, you can, I could check some heavy rainfall at the Kyushu district, and this is the rainfall distribution real time, and surely we can check some estimated rainfall distribution for 30 minutes later or 1 hour later or something. Maybe I'm not sure, but and this is the calculated by the meteorological agency. That's the degree of the dangerous of the slope failure or sediment failure, and this is purple area is a very dangerous situation now. Or this is heavy rainfall information like this, and this is the flood information. At that time, Komagawa River is flooded, and it is automatically released through the internet that this is now flooded. All right. So this is my smartphone, the wallpaper, and this page I collected some meteorological information for weather forecast for Amedas Fuchu, Amedas Sagamiko, or this is the Kikikuru or something, and some rainfall distribution now or something, and you know that this is some catfish. And in Japan, earthquake will be happening when the catfish is moving. So this is the earthquake information. So this application can automatically show when the earthquake happened. Then earthquakes happen, then it instantly shows the degree of the earthquake seismic wave, seismic degree. So I use this information through smartphone like this. So only 5 minutes, and the roads for natural disasters. So okay, this is just the information about the Japanese roads for the natural disasters, and it's very old season. We have the erosion control laws at the Meiji era, and this is a little important one. 1961, we have the Basic Act on Disasters, and this previous year, 1960 or 1959, we have the very severe typhoon, Isewan typhoon, Isebei Ise-1, we call this the Ise-1. Ise-1 typhoon hit in 1959, and the basic action of the disaster was published in 1961. This is in Japanese, 災害基本法 in Japanese, basic act on disaster. And this law determined that the lawyer, mayor of the city will be will in charge of the natural disasters. So they have to say, make alert or evacuation. So this is some basic law. And yes, surely we have many roads. And the 2000, just 2000 there, we have the Landslide Disaster Prevention Act. And from this, we need to make the hazard map. This is the published at this law. And this law decided that we need to make hazard map, and we means that some mayor or some government have to make the hazard map, and the government has to publish it. So that is the Landslide Disaster Prevention Act. So we have these laws in Japan. ちょっともう時間がなくなっちゃったな。And very sorry that we have no time now. And 2021, we have some debris for Atlanta, Mississippi. And this is some sample of the debris for disasters. And yes, this is the top of, this is a site that the debris flow happened, and debris flow forward to the sea. And this is the hazard map, debris flow, a sediment disaster hazard map, for example. And yes. So we can see the some orange line. That orange area is some disaster, potentially disaster area for debris flow. So at that time, debris flow start from here, but the sediment will move just like this orange line. So hazard map is very important to check. So sorry to rapid. And this is the last slide that I want to show you, that this time, this class, we will learn about some natural disasters, mainly induced by the heavy rainfall. That means induced by water. But we have many natural disasters that I cannot explain detail, but we know that for example, volcanic eruption, and after that we have volcanic debris, and especially we have in Japan too, and earthquake and tsunami after earthquake, and for example, drought or tornado or glacier dam break. It's now global warming means some melting of the ice and glacier. So some glacier will be collapsed with the much of the water. So that is a very dangerous one. And yes, this is a meteorite impact. Yes, actually, this is some natural disasters. And we cannot learn about these natural disasters. Drought is some kind of the meteorological one. So we could learn a little bit of this, but surely we need learn more about the natural disasters. So, but sorry, I don't have much time, and I'd like to show you about some basic meteorologically, and that is very important for the environment or circumstances, and in the near future, we have some climate change. So basic meteorological is necessary, but we need to learn more about natural disasters. Okay, so this is just finishing time. Thank you very much for attending. Thank you. ありがとうございます。And I have I send you the last report that through the なんだっけ、まあいいや。please answer that report. And ジュンさん and 誰だっけ、Ames students have to answer the report maybe surely until early December, because I have to check the score for you. So one week more. So and if you did not send the previous reports, please send it to me until early December. Okay. はい。じゃあ、これで、おしまいとなりますので、Thank you very much for attending. So, this is the last class today. Thanks for attending. はい、ありがとうございました。ありがとうね。